Hi everybody, welcome back to Quantitative Reasoning. Today we're starting Chapter 12 and we're going to be in Section 12.1, which is Sampling, Frequency Distributions, and Graphs. We have 4 objectives for today. First, we're going to talk about describing the population whose properties are to be analyzed, and we're going to talk a little bit about selecting an appropriate sampling technique. And then we're going to look at different ways to organize and present data, and this is really where we'll put most of our attention today. And then our 4th objective is to look at some ways that visual displays of data can be deceiving sometimes if we're not on our toes. So let's go ahead and get started. So first of all, what is statistics? Well, statistics is the branch of mathematics that is concerned with gathering, displaying, and analyzing data. That's all statistics is. It's just a way to get information from raw numbers and communicate that information effectively to the people who need to use it. Now, usually in statistics, we're trying to find out something about a population. So what is a population? A population is the set containing all the people or objects whose properties are to be described and analyzed by the data collector. So, for example, we might want to find the average height of all 8-year-olds in the United States. And so all the 8-year-olds in the United States would be our population. Or we might want to find the average income of teachers who have 10 years of experience in Mississippi. And so in that case, our population would be teachers who have 10 years of experience in Mississippi. So that's what we mean by a population. Now, usually a population is so large that we can't directly get data from every member of the population. And when that happens, we have to work with a sample. A sample is a subset or subgroup of the population. And so one of the main purposes of statistics is to gather data from a sample and use that data to draw conclusions about the larger population that the sample represents. So let's go ahead and look at example 1. It says, a group of hotel owners in a large city decides to conduct a survey among citizens of the city to discover their opinions about casino gambling. Describe the population. Now, the population is everyone whose opinion we're interested in understanding here. And it said that they wanted to conduct a survey among citizens of the city. So they're interested in the opinion of citizens of the city. So that's our population. All residents of the city are our population. And then in part B, one of the hotel owners suggests obtaining a sample by surveying all the people at 6 of the largest nightclubs in the city on a Saturday night. Each person will be asked to express his or her opinion on casino gambling. Does this seem like a good idea? Now remember, you want your sample to reflect your population. The people in the sample should represent a cross-section of the population. And if we only talk to people who are in a nightclub on Saturday night, that does not seem like it's going to represent everybody in the city, because not everybody goes to a nightclub on Saturday night. So for one thing, you probably wouldn't get parents of small children, because that's not where they are on Saturday night. For another thing, you might not get retired people. And what about economic background? It costs money to go to a nightclub on Saturday night. So lower income people may not be properly represented in this sample. So this actually would not be a good sample. And this kind of sampling where we just get to whoever's easy to get to and include those people in our sample, that's called a convenience sample. And a convenience sample is never a good idea because it never properly represents the whole cross-section of the population. So let's write, no, this is a convenience sample. By surveying only patrons of nightclubs, large segments of the population will be excluded. So that brings us to random sampling. Ideally, the members of the sample should be chosen at random so that we're not over-including or under-including any particular group of the population. We want every element in the population to have an equal chance of being selected for the sample. So in random sampling, each element in the population is identified and usually assigned a number, and the numbers are generally assigned in order. So for example, if our population included 100 people, we would have a list of those people and we would just number them all 1 to 100. And then we would randomly choose however many people we need to include in our sample. And the best way to get a sample from a large numbered population is to generate random numbers using a computer or a calculator. You know, if you just had a small population, like maybe less than 50 people, you could just put names in a hat and draw names out of the hat, and that would be random. But with a large population, it's not practical to put everyone's name actually in a hat. So what we do is we number the list of all the people in the population, and then we use a computer or calculator to randomly choose some of those numbers. Now, a lot of times, if you watch the news on TV or listen to podcasts or radio, they'll talk about call-in polls. These are not random because if people are calling in and expressing their opinion, those people are including themselves in the sample. And that is not a good way to get a random sample of the population, because what happens is people who call in are more likely to have feelings about an issue that are consistent with the show's host. If the show's host says they are for a particular candidate or against a particular candidate, then the people that call in will tend to have strong feelings, and a lot of times they agree with the host. Some of them might disagree, but they would have to disagree pretty strongly to bother to call in. And if they disagree with the host, they're probably not listening to that TV show in the first place, right? So the bottom line is, for a poll to be accurate, the sample must be chosen randomly from the larger population. We want to avoid self-selected samples like call-in shows, and we want to avoid convenience samples like saying, well, I'm just going to survey all the people in this particular apartment complex. Okay, so here's example 2, and we're talking about selecting an appropriate sampling technique. So let's go back to the hotel owners in the large city who are interested in how the city's citizens feel about casino gambling. Which of the following would be the most appropriate way to select a random sample and why? So choice A, we randomly survey people who live in the oceanfront condominiums in the city. Or choice B, we survey the first 200 people whose names appear in the city's telephone directory, if you can even find one, right? And then choice C, we randomly select neighborhoods of the city and then randomly survey people within the selected neighborhoods. So we want to choose the one that's going to give us the best cross-section of the population. And of course, that is going to be choice C. What's wrong with choice A is there's just one economic class of people who live in the oceanfront condominiums. So you're going to leave out large sections of the population if you only talk to people who live in oceanfront condominiums. And the problem with choice B is that if you only go with the first 200 names in the phone book, you have no idea if those people are going to represent the population well or not. Are they all rich? Are they all poor? Do they all live on the east side of town? Do they all live on the west side of town? We don't know. And so if we just go with the first 200 names in the phone book, that's called a convenience sample. We didn't put any work into making sure that the sample represents the population. And remember, convenience sampling is always bad. But in choice C, we're randomly selecting neighborhoods, so we're going to get all different economic backgrounds from all different parts of the city, and then we randomly survey people within the selected neighborhoods. So even within the selected neighborhoods, we might not get to talk to everybody, but we make sure that we randomly survey people. In other words, you just don't knock on the doors where the flowers in front of the house are nice and you feel like those people are going to be friendly. No, you have to randomly survey people so that you ensure that you're not creating bias in the survey by only talking to people that you think are going to be easy to talk to. So a random sample must give each citizen an equal chance of being selected. So just to kind of summarize what we've been trying to say here, surveys and polls involve data from a sample of some population. We hardly ever can survey everybody in the population. We almost always have to go with a sample. And regardless of the sampling technique used, The sample should exhibit characteristics typical of those possessed by the larger population. So, like I've been saying, if your population is 40% men and 60% women, then your sample needs to be 40% men and 60% women. If your population is 10% very wealthy and 20% very poor, then your sample needs to contain 10% of people that are very wealthy and 20% that are very poor. Your sample needs to represent your population, and so this type of sample is called a representative sample. And that's always what we want when we're choosing a sample. We want a representative sample. Otherwise, the data you collect is no good. So here's example 3. It says, the government of a large city needs to determine whether the city's residents will support the construction of a new jail. The government decides to conduct a survey of a sample of the city's residents. Which of the following procedures would be most appropriate for obtaining a sample of the city's residents and why? Okay, choice A. We survey a random sample of the employees and inmates of the old jail. Now, to be honest with you, I don't like choice A already because we're only sampling the opinion of people who were involved in the old jail. And who's our population? It said they wanted to determine whether the city's residents will support the construction of a new jail. So the population is the city's residents. If you only survey people who were involved with the old jail, then I'm sure that they have very valid opinions, but their opinions are not the only ones that we're trying to find out. So choice A is out. That's not going to be a representative sample. Let's look at choice B. Survey every 5th person who walks into City Hall on a given day. Well, I don't know. Those people might be a representative sample, but they might not. This is a convenience sample. We're not really having to do any work. We're just going to go sit at City Hall, and luck will determine who walks in and who doesn't. And so this is also not going to be a representative sample. Choice C. Survey a random sample of people within each geographic region of the city. Now, I do like this idea because we're going to get a random sample of people from all different parts of the city. So right now I'm leaning toward choice C. And then let's look at choice D. Survey the first 200 people in an alphabetical online listing of the city's residents. No, I'm going to say this is not a good idea. This is another convenient sample, and we just have no way of knowing if these 200 people are going to accurately represent the population. So choice C is our most appropriate choice, and the reason is that C is the only choice that guarantees representation for all parts of the city. Okay, now what do we do with data once we collect it? Well, a piece of data is called a data item or an observation. Once the data is collected, it can be presented using a frequency distribution. And a frequency distribution has 2 columns. We put the data values in one column, and then in the other column we label that frequency, and that tells how many times that value occurs. You've seen tables like this before. You just may not have called them frequency distributions. But we'll have the data values in the left column and the frequency in the right column. So here is example 4, and we are going to make a frequency distribution for this data, and this data is the age of maximum yearly growth for 35 different boys. So these 35 boys are a sample, and these numbers are the age at which they had the most growth. So since these represent ages, we're going to label this left column age, and this rightmost column is going to be the frequency. Now the column in the middle, I'm going to label tally. I've put it in blue because this column is basically just scratch work. It is not really part of your finished table. The finished table that you would actually present to your audience would be the left column, which is the ages, and the right column, which is the frequency. You wouldn't necessarily need them to see how you counted everybody up, okay? So what we're going to do here is just make a list of ages from the smallest age to the largest. Now, even if a particular age is not represented in this list of data, I still would need to include it here. So the numbers in the left column need to go from the smallest value to the largest value, not leaving any out, because if there are gaps, we need to be able to see them. So let's look through this table and just find the smallest number. I see a 10. 10 looks like maybe the smallest number that we have. And then what is the largest number? I believe the largest one I see is 18. Okay, so I'm going to put ages in the left column that go from 10 to 18. And now what we're going to do is just start with the top left number in the list and put a tally mark next to each number as it comes up. So my first number is 12. I'll cross that off my list and I'll put a tally mark next to the 12. Okay, see that? And then the next number is 14. So cross that off and put a tally mark next to the 14. Then do the same thing for 13. The same thing for the next 14. So now 14 has 2 tally marks. Then do the same thing for the next number, which is a 16, a 14. So now we have 3 14s. Now do the same thing for the next 14. And on the next row, we have a 17, a 13, a 10, another 13, 18, 12, 15. Okay, so you can see where we are here. Now the next number is a 14. We've already got 4 14s. So when you're making your tally marks, every 5th one you want to put diagonally, and that will help you count them up easily later. So this is my 5th 14, so I've put a mark across the other 4 marks. Okay, now 15 is my second 15. This is my third 15. Now I get 2 more 14s. So I'm going to put 2 more tally marks here. See that? And then another 13 and another 15. Okay, now I'm just going to go ahead and do the rest of the table, and I'm going to trust you to do the rest of the table on your own as well. Okay, now that I have tallied up all the values from the table, I'm ready to count and get my frequencies. So the frequency is the actual number. Remember, at this point, the frequency distribution is not finished because anybody who's reading this table might not know what your scratch work means. You need to give them an actual number here. So for the age 10, we had a frequency of 1. For age 11, we had a frequency of 2. For 12, we had a frequency of 5. Then for 13, it was 7. For 14, it's 9. For 15, it's 6. Then 3, 1, 1. And so here is our frequency distribution, and the only parts that matter are the ages in the left column and the frequencies in the right column. Now, just to make sure that we didn't skip any values or accidentally record something twice, it is always a good idea to add up these numbers. So at this point, I would want you to say 1 plus 2 plus 5 plus 7 plus 9. Get the sum of all the numbers in the frequency column, and for us, these frequencies add up to 35. And the reason that matters is the sum of your frequencies should match the number of data values you had in your list. So we have 35 values here, and we have 35 values in our frequency distribution, so we can feel pretty confident that we did it right. Now let's look at example 5. Construct a frequency distribution for the data showing the final course grades for students in a pre-calculus class. Okay, so we know how letter grades work. The grades are going to go from A to F. Let's go ahead and set up our table. These are grades, so I'll label the left column grade, and then the middle is going to be our tally marks, and the right column is going to be our frequencies. And like we said, grades go from A to F, so A, B, C, D, F in the left column. And now let's do our tally. So the first grade in our list is an F. We'll put a tally mark next to the F and cross that off. The next grade is an A. Put a tally mark and cross it off the list. The next 2 are B's. So put 2 marks next to the B and cross those off, and then we get a C. For the next row, we've got C, B, C, A, A. So I'm going to go ahead and put C, B, C, A, A on my table and cross each of those off. And I'll let you do the third row on your own and the fourth row. So when you get finished with all 4 rows, this is what your tally marks should look like. And then our frequencies are that we had 3 A's, 5 B's, 9 C's, 2 D's, and 1 F. And just to be sure that we got all the data and didn't double count anybody or leave anybody out, let's add up our frequencies. So 3 plus 5 plus 9 plus 2 plus 1 all adds up to 20. And we can see that our list of grades was 5 by 4, so that's 20 grades, and so we feel pretty good that we got all the grades accounted for. Now let's talk about grouped frequency distributions. Usually there are so many numbers in our list that it does not make sense to list each number on a separate line. That actually makes it harder to see what the data are trying to tell us. So usually we need to group the data into classes. So this group from 15 to 19, this is our first class. The group from 20 to 24 in this table is the second class in this table. So again, when there are many data items, we usually end up grouping the data into classes. Now, one drawback of putting the data into classes is that it prevents the reader from seeing the original data. So when I look at this first class, I know that there are 443 people between the ages of 15 and 19, but I have no way of knowing if 300 of them are 15 and the rest are 19, or if some of them are 16, 17. There's no way to tell. So we do lose that. But what it does allow us to do is see the patterns in the data much more easily. So with them grouped in this way, I may not know every person's individual age, but I can see that the largest group is the group that goes from 30 to 34. And so it's helpful to be able to see that. Okay, so like I said, each range of numbers in the left column represents a class. So in this particular table, we have 1, 2, 3, 4, 5, 6, 7, 8 different classes. And notice that there are no gaps between the end of one class and the beginning of the next class. Every age should fit into one class, and exactly one class. So notice that the first class ends at 19, but the second class starts at 20. And all the classes are like that. This class ends at 34, but the next class begins at 35. So everybody is going to fit into exactly one class, and that's what we need. So we need no gaps between the end of one class and the beginning of the next. Now, for every class, there's a range of numbers, and the first number in that range is called the lower class limit. So for this first class, the lower class limit is 15. For this class, the lower class limit is 40. The first number in each class is the lower class limit, and the last number in each class is called the upper class limit. So our upper class limits are 19, 24, 29, and so on. The class width is the difference between consecutive lower class limits. So in this case, the class width is 5. Notice that the difference between these two lower class limits is 5. 20 minus 15 is 5. And no matter which two classes you pick, the difference between any two consecutive lower class limits is always 5. This one goes from 40 to 45. This next one goes from 45 to 50. So in this case, the class width is 5. Now, it's confusing for a lot of students, so I want to make sure that you understand. I think when we say class width, we usually, when we think of width, we think of something going across. And so a lot of students want to say that the class width here is 4 because 19 minus 15 is 4. And I think the word width makes them want to look this direction. But that's not the way it works. Class width is the difference between consecutive lower class limits. So the class width here is 5, not 4. Okay, here's example 6. It says use these classes, 40 to 49, 50 to 59, etc., to construct a grouped frequency distribution for the 40 test scores shown below. So let's go ahead and set up our frequency distribution. And so I've got 3 columns. I'm going to have scores in the left column, so let's label that score. I'm going to have tally marks in the middle and the frequency total on the right. Now they told us what classes to use here: 40 to 49, 50 to 59, 60 to 69, and so on. And every number is going to fall into exactly one class. So let's go ahead and tally those up. The first number in our list is 82, and so that's going to fall in the class from 80 to 89. So let's put a tally mark there and cross that first number off of our list. The second number is 47, so cross that off and put a tally mark on the class that goes from 40 to 49. The third number is 75, so that's going to make us put a tally mark in the 70s. And I think you get it, so I'm going to go ahead and finish the rest of the first row. And when you finish the first row, yours should look like this. And now let's go ahead and do the second row. Okay, by the time you get to the end of the second row, you should have 5 numbers in the 80 to 89 class. So here's how my tally marks look at the end of the third row, and at the end of the fourth row, and at the end of the fifth row. And so our frequencies are going to be 3 scores in the 40 class, 6 scores in the 50 class, 6 in the 60s, then 11, then 9, and then 5. And by the way, one thing that stands out to me looking at this frequency table is that half of our values are between 70 and 89. Notice that these two numbers add up to 20, which is half of the numbers in our list. And so we had a lot of scores in the 70s and 80s. Now let's answer some questions about our frequency table, and I've just copied the same table here so that we can see it. And part A says, what is the lower class limit for the second class? Well, of course, the lower class limit is the lower number in the range, and the second class is 50 to 59, so the lower class limit here is 50. And then what's the upper class limit for the fourth class? Well, the fourth class is the 70 to 79, and so the upper class limit here is 79. And then part C, what is the class width? The class width is the difference between any two consecutive lower class limits. And so the difference between 50 and 40 is 10, and so the class width is 10. And by the way, to determine class width, we usually look at the first two classes, but you should be able to look at any consecutive pair of classes and see the same class width. Now, here is example 7, and I know this looks like a huge list of numbers, but let's just see what we've got here. The IQ scores of 70 students enrolled in a liberal arts course at a college are listed below. Construct a grouped frequency distribution for this data. Use 85 as the lower class limit of the first class, and use a class width of 5. So this time they're asking us to construct our own classes, and we can do it. It's not a problem. I've got our usual 3 columns here. The left column is going to represent these IQ scores, so let's go ahead and label that left column IQ, and the middle will be our tally marks, and then our frequencies on the right as usual. Now they said to use 85 as the lower class limit for the first class. So let's put 85 right here. And then they said use a class width of 5. So that means that the next lower class limit is going to be 85 plus 5. So the next lower class limit is going to be 90. Now that we have that, let's go back and put the upper class limit of the first class. If the second class starts at 90, the first class needs to end at 89. So our first class goes from 85 to 89, and from here out we can get all the rest of the numbers by adding 5 to the previous number. So 89 plus 5 is 94. Now for the next class, just add 5 to both of these numbers. 90 plus 5 is 95. 94 plus 5 is 99. And there's our third class. Now how far do we have to keep doing this? Well, the answer to that is that the largest number in our list needs to fit into our largest class. So let's kind of look through this list. I see 120 right here, and let's kind of glance through. Oh, here's 124, and so far 124 is the largest that I see. Okay, that's it. So we need to keep going until we get a class large enough for 124 to fit into. So let's add 5 to each of these class limits. And the next class will go from 100 to 104. And then add 5 again. The next class goes from 105 to 109. And keep going until we get a class where our largest data value fits. And so the last class that we need is going to be 120 to 124. Okay, now we're not going to go through all of these individually. I feel like everybody probably gets how to sort the data into the different classes, so I'm just going to do it a row at a time. At the end of the first row, this is what your tally mark should look like. And then at the end of the second row, and then at the end of the fourth row, it should look like this. This is the end of the sixth row, end of the eighth row, and then the end of the table. And so our frequencies are going to be 2, 5, 12, 14, 15, 11, 8, and 3. And so this is our finished frequency distribution. And so what do you notice about this frequency distribution? The thing that I see is that a lot of the values are occurring in the middle classes, and there are not a whole lot of values that are in the very low classes or the very high classes. So most of the IQs fell into this middle range. Now, just to double check ourselves that we didn't skip over any values, we should total up the frequencies. So if you add up 2 plus 5 plus 12 and so on, add up all the frequencies, you should get 70, and we did here, so that's good because we had 70 numbers, of course, in our list. So once we get a frequency distribution built, what can we do with it? Well, one of the things we can do is take it and turn it into a graph, because we know a picture's worth 1,000 words. Now, a graph that looks like this is called a histogram. Notice that we have numbers on the horizontal axis and then numbers on the vertical axis, and the bars touch. So a bar graph with bars that touch, it's very important that they touch, can be used to visually display the data from a frequency distribution. This is called a histogram. The bars will touch, there will be numbers on the horizontal axis, and this is called a histogram. Or, instead of using bars, we can just put a dot at the height where each bar would have been, and then connect the dots, and this is called a frequency polygon. A line graph called a frequency polygon can also be used to display the same information. Both of these graphs came from the frequency distribution that we built back in example 4, where we were working with the 35 boys' age of maximum yearly growth. Now, there are two ways that we can label the horizontal axis. The numbers on the horizontal axis can either represent class limits or the middle number in each class. And if you remember, with this particular frequency distribution back in example 4, there was only one number in each class. And so you see that like the bar is centered over that number, and the number appears in the middle of each bar. But if you have classes, then you can have the lower class limit represent the left side of the bar and the upper class limit represent the right side of the bar. Sometimes you'll see histograms that are labeled that way. And then the numbers on the vertical axis represent the frequencies. The numbers on the vertical axis represent the frequencies. And notice that the vertical axis only needs to go up as high as the tallest bar, or the highest point if you're using the frequency polygon. So these are two very common graphs that you see made from frequency distributions. Now let's make our own histogram from this frequency distribution. So just to give you a flavor of how it's done. So we know that the numbers from the left column are the labels that we put on the horizontal axis. So let's go ahead and put a tick mark on the horizontal axis for every number from this left column, and we'll go ahead and label these 10 through 18. Now for the vertical column, we know that our highest bar is going to be 9 units tall. So we need our vertical axis to be labeled up to 9. What I've done here is I've just counted by 2 because that was easier. It's okay if it goes a little past 9. You just wouldn't want it to go up to like 20 or something, because then your histogram would be all squashed down in the bottom of your table. But it can go up to 10, that's fine. And so I've got these tick marks representing the even numbers, and I just went ahead and put smaller tick marks in between to represent the odd numbers, but I didn't label them because when you're doing this by hand, it can get really crowded and hard to read. So I think if we just have the even ones labeled here, everybody will probably be able to infer that this is 1, 3, 5, and so on. Okay, now, this is a histogram, so the bars are going to touch, and the height of each bar will represent the frequency for each particular class. And we also want to try to be careful to keep the bars as close to the same width as possible. Now, I know that we're drawing by hand, so we're not going to get out a ruler or anything here, but as much as you can, you want to keep the bars the same width, and you want to keep them centered over the number that they are matching up with. So my first bar is going to be 1 unit tall, and it's going to be centered over the 10. So that's my first bar. Now my second bar for the 11 class needs to be 2 units tall. So it will be about 2 units tall, and it will be centered over the 11. It's going to go right here. And so that's our second bar. And then let's go ahead and get the third bar. It's going to be 5 units tall, centered over the 12. So maybe up to here. And then the bar for 13 is 7 units tall. The bar for 14 is 9 units tall, and so on. 6, 3, 1, 1. And so these last two are the same height, and it's okay if they blend together a little bit. I have outlined mine in a different color so that you can still see, but it's okay if they're all the same color. And now let's draw a frequency polygon for the same data. So the horizontal axis will have the same numbers from 10 to 18, and we do need to label the numbers. And again, the highest point is going to belong to the 14 class, and it's going to be 9 units tall. So we need our vertical axis numbered at least up to 9, and we can do it just like we did last time and go up to 10. And just for convenience, I'll fill in marks in between the even numbers to represent the odd numbers. Now this time, because we're doing a frequency polygon, we're just going to put a dot at the proper height for each class. So for the 10, the dot goes at a height of 1. So there it is. For the 11, the dot goes at a height of 2. So it'll go about right here. For the class of 12, the dot should go at a height of 5. Then 7, 9, 6, 3, 1, 1. Now, here's the thing about frequency polygons that you might not notice until you draw one by hand, and that is we connect the dots, but we don't start with the first dot. Really, we go back one number before that, which in this case would be back to what looks like the origin, and we start there and go up to that dot. So it always has to touch the horizontal axis. So from back here, we draw a line from the horizontal axis up to the dot, and then just a straight line to the next dot, straight line to the next dot, and so on. It's going to look really weird. You're just connecting dots. Don't smooth it out or anything. And then connect, connect. And then for this last one, the dot is over the 18 class. Remember, the last class was 18. And so the next line segment needs to go back down to the horizontal axis about where the next number would be, which would be 19, and it would be about right here. So just draw it back to the axis like that. And that way we have a frequency polygon. See, the word polygon should make you remember that it has to be a closed shape. So it needs to touch the horizontal axis on both sides. So it's kind of closed up. All right, now we're going to actually look at a frequency polygon and answer some questions about it. So this is example 9, and it says the frequency polygon shows a distribution of IQ scores. Use the graph to determine whether each statement is true or false. If the statement is false, correct the statement to make it true. And then part A, the graph is based on a sample of approximately 50 people. Well, let's see. We know that for each dot here, the height of that dot represents the number of people in that class. So what we can do is just add up the height of each of these. So this class right here where the score is 70, it looks like I'm thinking maybe 2 people in that class because the 5 dot would be up here. And so I'm thinking maybe 2, and maybe this is 3. It's hard to tell if this is representing 1, 2, or 3 people, or maybe 4, who knows. But anyway, right here where it's right on the line, we know that this third class represents 5 people, and we know that the next dot represents 10 people, and the next dot after that represents 20 people. There were 20 people who had this particular IQ score. And so we'll add 20. The next one is 25. The next one is somewhere between 25 and 30. I'm going to say 27. And then another 25 and 20 and so on back down to the last class. And these two look like the first two, so I'm going to say plus 3 plus 2 on the end. Now if you add all of these numbers up, it comes out to about 157. So it's not correct to say that the graph is based on approximately 50 people. We counted at least 157 here. So let's say that the statement as they gave it is false, and we'll correct it by saying that the graph is based on approximately 157 people. Then for part B, they said more people had an IQ of 100 than any other IQ score. So again, let's go back to the frequency polygon and let's see. Here is an IQ score of 100, and when I follow that up, sure enough, that dot is the highest one, which means there are more people with that IQ score than any other individual score. So that statement is true. And then part C, as the deviation from 100 increases or decreases, the scores fall off in a symmetrical manner. So they're claiming that as we move away from 100, the shape of the graph is the same on both sides. And I believe that is true, because if you look right here where the score of 100 is represented, the shape going in either direction is the same. So part C is a true statement. Then for part D, more people have an IQ score of 110 than a score of 90. So let's look. The score of 110 looks to have about 20 people, and a score of 90 also looks to have about 20 people. So we're going to say that statement is false because the number of people with a score of 110 is about the same as the number with a score of 90. And then for part E, it says the percentage of scores above any IQ score is equal to the percentage of scores below that score. Well, let's go back and look at our frequency polygon again. So remember that the height of each of these dots represents a group of people. So if I wanted to talk about the percentage of people who have a score that's 120 or more, that would only be these maybe 10 people or so out of the whole 157. So something a little less than 10% for the people who have a score that's 120 or better. And that means that 90% or more have a score that's less than that. So it's not true to say that the percentage of scores above any IQ score is equal to the percent below, because it can vary depending on which IQ score you want to talk about. Now, if we pick 100 right in the middle, see, the number of people who have an IQ score less than 100 looks to be about the same as the number of people who have an IQ score more than 100. And so to make this a true statement, we're just going to say that the statement is false first. And then to make this a true statement, we need to say not any IQ score, but a score of 100. And so let's say that the percentage of scores above 100 is the same as the percentage of scores below. Now let's take a look at stem and leaf plots. And these are really easy to make and really easy to understand. So let's take a look. A stem and leaf plot is constructed by separating each data item into 2 parts, a stem and a leaf. Now all of the data that we will be working with is 2-digit data. So for us, the stem will always consist of the number in the tens place, and the leaf will always be the number in the units place, or sometimes we call it the ones place. Now we're going to look at an example in just a minute, but I want you to know that when you are listing the stems to make your stem and leaf plot, all of the numbers between the smallest stem and the largest stem should be included in the plot. And then before you type your leaves into MyLab, make sure that you put the leaves in order. All of the leaves should be put in order from smallest to largest. That's important. Now before we actually make a stem and leaf plot of our own, I wanted you to look at a couple and see how they're made so you can understand what we're going to be doing in just a minute. So let's pretend that there's an ice cream store out there that has not been doing any advertising, and they have written down their sales each hour for the last 36 hours that they were open. So maybe they're open 12 hours a day, and every day for 3 days they wrote down their hourly sales at the end of each hour. So here is what the stem and leaf plot would look like. This represents 36 numbers, and remember these numbers on the left, these are called the stem, and these represent all the tens digits from the original data. These numbers on the right are called the leaves, and these represent the ones digits from the original data. So right here where we've got a stem of 1 and a leaf of 3, that represents a data value of 13, 1, 3. Right here where we've got a stem of 4 and a leaf of, say, 8, that represents a 48 from the original data. Notice that the stem of 2 has no leaves, and that just means that in the original data set there aren't any numbers that are 20-something. So there are no numbers in the original data that have a 2 in the tens place. What do you think these numbers here represent where the stem is 0? These would be our single-digit numbers. So this would mean there was 1 hour where they had no sales, and there were 2 hours where they only had 1 sale, maybe early in the morning or something. And then there was an hour where they had 2 sales, an hour where they had 3, and an hour where they had 5. So now let's take a look at the original data. Okay, notice that all of our leaves are in order. So when we look at these leaves, we see 0, 1, 1, 2, 3, 5, and that represents the first row here of our table, 0, 1, 1, 2, 3, 5. And then all of our team numbers are 13, 13, 13, 14, 17, 19, 19. So look over here at our leaves, and you can see how the numbers on this row all represent 13, 13, 13, 14, 17, 19, 19. And then over here in our data list, the numbers jump from 19 to 30. So that's why you don't see any 20s listed here. And then we have 30, 30, 31, and then we have 32 listed 3 times. So 2 30s, a 31, 32's listed 3 times, and so on. You can see now how the table works. And now notice that it's not necessary to put a comma or anything between the leaves. That's because each leaf can only have 1 digit. So it's not really necessary to separate the leaves because we know that each individual digit represents a number from the original data set. Now look what the stem and leaf has done for us. When you look at the original data set, you might not notice right off the bat that there are no 20s. But when we look at the stem and leaf plot, it's obvious that there are no 20s because that row is completely empty. So it kind of stands out to us. And another thing that stands out is we have more 30s than any other class of data. There are 10 data values in the 30s, but there aren't that many data values in any of the other groups. Now let's imagine that this ice cream shop does a little advertising, and so their sales improve. And so this is going to be their stem and leaf plot for 36 hours of hourly sales after they've done some advertising. I wanted you to see here what would happen if the numbers went above 2 digits. So look at the 9 stem here. You can probably see that the 90s are going to be 90, 91, 91, 92, and 94. And then on the next row, we have a 2-digit stem. It's okay for a stem to be 2 digits, but a leaf always has to be only 1 digit. So this leaf right here would represent 102. This leaf would represent 106. And then on the last row, this leaf would represent 110, so 110, and this leaf would represent 113, so 113. Let's take a look at the original data. So you can see that the 50s are 51, 52, 57, 58, and that's what we see here in the original data list. And when we look at the stem and leaf plot, you can see that we have more data values in the 70s than any other group, and you can see that we have 5 numbers that went over 100. So here's our 102, 106, 107, and you can see those here in the original data list, and then our 110, 113, and you can see those here. So are you ready to make your own stem and leaf plot? Here we go. So this is example 10, and it says the data set below shows test scores for 40 statistics students. Construct a stem and leaf plot of the data set. And so we know that the first thing we're going to need is a vertical line that we're going to use to separate our stems from our leaves. Now, to figure out what stems we need, we have to look through our original data list and find the smallest number in the tens place. So I see 80 something, 40 something, and if you keep going looking only at the tens digits, you'll see that the smallest data value we find in the tens digit is a 4. So that will be our first stem. And then we know that we need to include all the numbers from that first stem down to the largest one. And so let's look through our data list for the largest number in the tens place, and it's going to be this 9 right here. So we're going to go ahead and list all of the tens digits from 4 to 9, and these are our stems. Now, very similar to the way that we made our frequency distributions, what we have to do now is just go through the data list one value at a time and put each leaf on the correct row. So right here where our first data value is 82, the stem for this number is 8 and the leaf is 2. So we need to go down to the row where we have our stem of 8 and we'll put a leaf of 2. And this is going to represent 82. And then we can cross that off of our list. For the next number we have 47. So the stem is 4 and the leaf is 7. And so we'll come up here to where the stem is 4 and we will list a leaf of 7. And we'll just keep going like that. So for the 75, we're going to go to the 7 stem and list our 5. Cross that off the list. And then for the 64, we're going to come to the 6th row and put a 4 and cross that off the list. Now I think you've probably got the idea. So for the rest of this row, I'm not going to do each individual one, but I'm just going to go ahead and do the next 4 values. And when we get to the end of the first row, your stem and leaf plot should look like this. Now let's go ahead and do the second row. And so when you get to the end of the second row, you should have this. Then at the end of the third row, you should have this. And then here's the 4th row. And here's the 5th row. Now, of course, we are not quite finished with this stem and leaf plot because the leaves are not in order yet. And it's very important for you to put the leaves in order. For one reason, when you're doing your MyLab homework, they won't give you credit for it. They won't mark it correct if the leaves are not in order. But also, just as a practical matter, if you ever needed to make a stem and leaf plot for someone else to look at, it's very helpful to the reader if you'll go ahead and put the leaves in order. See, you've already got the numbers somewhat in order because right here you have all the 40s, right here you have all the 50s, and so on. So your data is almost all the way in order. It's just nice to go ahead and finish it up. So let's do that. Now here is our stem and leaf plot that we already have made, and all we're about to do now is just take those same stems, but for each set of leaves, we'll just put them in order from smallest to largest. So the leaves for the data values that are in the 40s will be 3, 5, 7, just taking these same leaves and putting them in order from smallest to largest. The leaves for the data values that are in the 50s will be 0, 4, 6, 7, 7, 9. Now what I like to do is count them up and make sure that I didn't miss any. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And that way you don't miscopy anything. Okay, for the 60s, Our leaves in order will be 3, 4, 6, 6, 7, 8. And then here are the 70s in order. Here are the 80s in order. And then here are the 90s in order. And so here is our finished stem and leaf plot. Now, what does this stem and leaf plot help you see that you could not necessarily know from just looking at the list of raw numbers? Well, one thing that it helps me see is that there are more data values on this higher end of the table than there are at the low end. There are only 3 data values in the 40s, but there are lots of data values in the 70s and 80s and even several in the 90s. And if you could take this stem and leaf plot and turn it on its side, where each row of the stem and leaf plot represents a bar on your histogram, you could see that the tallest bar would be the bar for the numbers that go from 80 to 89. And then the 70s bar is almost as tall as the 80s. Now, just a couple more things to keep in mind about stem and leaf plots. A stem and leaf plot can help us see the distribution of the data with a class width of 10. So, we don't always want to take the time to draw a real histogram, but if you just put the numbers in a stem and leaf plot, that's sort of a histogram with a built-in class width of 10. So that's kind of neat. And then one advantage of a stem and leaf plot over a histogram is that the stem and leaf plot preserves the original data values where the histogram does not. If you're looking at a histogram, you're just seeing bars and you can't know what the original data values were, but when you're looking at a stem and leaf plot, you still can get back to those original data values if you need to. Now, one problem with graphs is that a lot of times they can distort the underlying data. Sometimes the graphs that people make distort data because the people don't know how to make a graph properly, but sometimes it's done on purpose to trick people or make them think something that's not really true. One thing that can really mess with the way we see a graph is what people are doing with the vertical axis. So both of these two graphs are from the same data. They are both graphs that represent this table that you see in the middle. The vertical scale on the left is stretched out. Notice that it goes from 10.5 to 13.5. So when you draw the line graph, it looks like there's this huge vertical drop. And so it looks like the poverty rate is going down really fast, but it's not really. So to fill in your blanks, the graph on the left stretches the scale on the vertical axis to create an impression of a rapidly decreasing poverty rate. But the graph on the right may have compressed it too much. Notice that this vertical scale goes from 6 to 18. And so the data on the graph are actually kind of squashed here into the middle, and there's a lot of blank space both above and below the line. So this may not be the best vertical scale either. So I'm not really saying that one of these is right and one of these is wrong, but I am saying that if you stretch out the vertical axis, it makes it look like the poverty rate is rapidly decreasing. If you compress it, it looks like it's slowly decreasing. And so you as a reader need to be aware of what's happening with the vertical axis so that you're not tricked. So when you see something changing really fast here, ask yourself, is it really that big of a change? And if you look at the numbers, you can see, oh, well, it really only went from 13.5 to 10.5. So it's not that big of a change overall, even though it looks very big. And if I saw this graph on the right, I would ask myself, why is there so much blank space above and below? Like, what is going on with the vertical axis? So here are a few things to watch out for when you're looking at a graph. One, is there a title that explains what is being displayed? There should always be a title that tells you what you're looking at. 2, are numbers lined up with tick marks on the vertical axis that clearly indicate the scale? They should. Has the scale been varied to create a more or less dramatic impression than what the data actually shows? Maybe. You have to ask yourself that question and be aware if the person who made the graph is maybe trying to create a false impression. 3, and this is a big one in the days of PowerPoint, and now that we have computers that can draw fancy graphs for us, are there too many design and cosmetic effects that draw attention from or distort the data. And we'll look at that in just a minute. And then 4, has the wrong impression been created about how data are changing because equally spaced time intervals are not used on the horizontal axis? You have to watch out when the horizontal axis represents time that from one tick mark to the next it should always be the same amount of time going by. And we'll see that in one of our next few examples as well. Alright, a couple more things to look out for. Are bar sizes scaled proportionately in terms of the data they represent? Remember when we drew our histogram we said try to get the bars about the same width. That's because all the classes are the same width, therefore the bars should be the same width. If they're not, it can mess with your visual perception and make you think that the class is bigger than it really is. And then finally, is there a source that indicates where the data in the display came from? Did they maybe make it up, or does the original data maybe not really say what they thought it said? Do the data come from an entire population or a sample? One thing we tend to do these days especially is look at data that represents a sample and then assume that it represents the entire population, but it may not. That's one thing we have to be careful about. So, was a random sample used? And if so, are there possible differences between what's being displayed in the graph and what's occurring in the entire population? Who is presenting this graph? And does that person have a special case to make against or for the trend shown by the graph? People will frequently distort data to try to make their point, and they may not do it on purpose, but we often find what we want to believe, and so you as the reader have to be aware if somebody is trying to persuade you to take on a certain opinion when they have a vested interest in getting you to adopt a particular opinion. Okay, so here are a few examples, and we're going to look at some examples of bad graphs and see if we can figure out what's bad about them. So here we have a graph of highest marginal income tax rate 2017 versus 2018. And one place you always want to look to see if the graph is being distorted is look at the vertical axis. In this case, the vertical axis only goes from 36 to 40, so it looks like a huge difference between the two. It looks like the 2017 tax rate was 3 times the 2018 tax rate. So what happened? Did the highest income group get a giant tax cut in 2018? Actually, not really, because if you look at the vertical axis, you can see that it only dropped from 39.5 down to 37. So yeah, they got a little tax cut, but not like 1/3 or anything like that. Just a little tax cut. And so what we would say here is that the 2017 bar looks 3 times as tall as the 2018 bar, and here is a graph that might be a better representation, but see, it doesn't get the emotional response that the distorted graph got. So here, because the vertical axis starts at 0, we can see that there is a small decrease from 2017 to 2018, but it's not giant. And here's part B. So what's misleading about this graph? Well, this kind of graph is really easy to produce on PowerPoint. I'm sure that you have made a 3D graph like this at some point in your high school career, or you've seen them in other people's presentations. The problem with the 3D is because the circle is kind of laid on its side, the 3D view distorts how we see these categories. So now look at the same graph in a 2-dimensional form. This is the same graph with the same data, but you're looking at the circle straight on. So when you look at the 3D graph, well, this red section right here, because it's closest to us, it looks very large, and it looks like it's by far the largest one to me. But then when you look at the red section over here on this graph, I know it's not in exactly the same position, but this is the same category, some college, no degree. Okay, so it's the same color. Now you can see that it's actually only 20%. It's actually less than a quarter of the circle, but it's hard to tell that when you're looking at the 3D view. And the largest section is actually high school diploma at 27%. but when you look at the 3D graph, it looks kind of small. It looks like less than a quarter when it's actually more than a quarter. So always be just a little bit leery of the 3D graphs. Okay, here's something that we see in online news stories a lot, these what they call pictograms. So what's misleading about this one? Well, if you actually look at the percentages and think about the numbers, 33% is more than twice as much as 15%. So its bar should be twice as big, but it's not. So the difference between the housing cost and the transportation cost is actually much greater than what you can visually see here. And so let's just say that the housing bar should be more than twice as long as the transportation bar. And you have to keep an eye out for things like this, especially on these pictographs, because they will often distort the bars just to make them fit in whatever picture they're trying to use. Okay, now let's look at part B of example 12. And so here we are looking at the number of square feet in an average U.S. single-family home. And it looks like they're showing us that home sizes have increased dramatically in the last several years. And so I have a couple of problems with this graph, actually. So the first one that strikes me right off the bat is we don't know whether we're supposed to be comparing the width of the houses or whether we're supposed to be comparing the height of the shadows, like do the shadows represent bars, like a bar graph, or are we supposed to be comparing the areas here? Because notice that as the height and the width grow at the same time, the area grows dramatically. If you thought that you were supposed to be comparing areas, which that's what your eye will naturally try to pick up on, if you thought we were comparing areas, then you would say, well, this area is about a fourth of this one, or maybe even less. Have home sizes grown by more than quadruple since 1980? But actually, if you were to calculate a percent increase based on these two numbers, you would see that housing sizes have only increased by 37%. So that's a big increase, but it's not like quadruple or anything. And so let's write down that our first problem is we can't tell by looking at the graph if we're supposed to be comparing the height of the shadow or the width of the house or the area of the shadow. We just don't know. And if we're not supposed to be comparing the height or the area of the shadows, then what are they there for? They're not really doing anything. And then my second problem with this graph is look at the years along the bottom. The first house is representing 1980 data, and the second house is representing 1990, and the third house is representing 2020. So always remember, when the horizontal axis represents time, it should always be a consistent amount of time from one bar to the next on your graph. So here we're jumping from 1980 to 1990, that's just 10 years, but the next one goes from 90 to 2020, so that's 30 years. So if anything, this house should be moved way out to the right because the amount of time from 1990 to 2020 is a lot more than the amount of time from 1980 to 1990. So we'll also write down that the difference between the years is not consistent. And one more here. This one is the purchasing power of the diminishing dollar. And so on this one, it looks like the dollar bills represent bars on a bar graph, and that would be okay. But again, we have kind of the same problem that we had with the houses, which is in order to keep the dollar bill looking like a dollar bill, they had to change the width of it. As the bar gets shorter, the dollar bill gets narrower, and your eye naturally perceives area. So this dollar looks way bigger than this dollar. And it is some bigger, of course, but because they are changing both the width and the height, it makes this one look way smaller in comparison. And so we'll just write down that the changing widths are misleading. And the other problem is also one that we saw with the housing example, and that is that the years are not consistent across the bottom. So we jump from 80 to 90, which is a 10-year difference, then from 90 to 95, which is a 5-year difference, and then this last one jumps from 2000 to 2020, so 20-year difference. And so whatever trend you think you're seeing here that your eye would naturally pick up on, it's not the real trend at all, because the years are not being kept consistent for us. So that's another reason this graph is misleading. The difference between the years is inconsistent. Okay, so those are some things to look out for as you see graphs all around you. They're not going away. Graphs are here to stay because, like I said, a picture's worth 1,000 words. So they're going to continue to generate graphs, and graphs can be very helpful. But you always want to critically look at the graph and be sure that it really does say what the person is promoting that it says. And then there were lots of other things we looked at in this section. I hope this has been helpful to you, and I'll see you guys again in section 12.2 next time. Bye-bye.